pleb, I try to point in the direction, could it be because the linear method that you will always get the same results? But the truth is, most of these methods will solve it numerically, which already can lead to some differences, but the key difference is actually, I will just stop this, we don't have to run this to the end. The key difference is that what you do in PCA is not uniquely defined in terms of the sign of the component. I will give you a brief intuition later on, but this is the implementation I got in PCA, and if I do this in SVD, so this is singular value decomposition using SciPy, I get the following eigenvectors. And if you just focus, let's say, on this component here, you can see that it swaps sign, right? I'm not very good at this. It swaps sign between the two different implementations. So that's a big problem if you want to make your results comparable, for example. And if you want to have a basic intuition for it, is that you, in PCA, you try to, for example, in singular value decomposition, there are basically two options for how you can define the eigenvector. It can show in two different directions, so to speak, right? And it will be compensated by the unitary matrix. There are different ways of looking at this, but if you, it just has to be consistent. So for example, if your sign flips for the eigenvectors that I just plotted, right? Then the time series will be represented, so the PC, the principal components themselves, the PC time series, will be represented by U times S, so that the time series will also flip sign. So what becomes a positive value before and becomes a negative anomaly. But it just has to be consistently flipped. But it's not clear which way around it should be, okay? So there are methods that we use, for example, to make it definite. I just uniquely defined an SVD flip method to make it always reproducible on different ways and numerical things. But unless you do this, basically what you inherit is different, basically numerical noise. Okay, so you will run through this in the assignment, so maybe I don't have to lose too much time on this, but you can plot the eigenvectors and you can plot accordingly by calculating x times v or u times s. You can calculate the time series, okay? You can already see that the time series partly look quite different for different components, and component 3 looks slightly odd here. I should probably check this out. I wouldn't know why this would be following such a different frequency spectrum to everything else. And you will see that this looks slightly odd as well if you do, let's say, a fast Fourier analysis where you can look at those time series and then recover return periods of different frequencies, so power spectra for different return periods. And what you might be able to see from behind is, found the Baxter, is that between year 10 to the 0 is period of 1 year, so this would be an annual cycle, but I mostly took this out by deseasonalizing the data. You see that the anomalies have this fairly high power, some of the time series between, let's say, 1 year and 10 years periods of variability. You should probably be careful based on 75 years of data what to interpret about to let's say 60 years or 70 year periodicities. So this might just be trends or tails. But there might be some sort of artificial artifact here that defines a very strong peak here at 8 years in time series 3. So that would be something that I wanted to look into and see if there might be some sort of problem with the data set I was using for this particular point. But the point is, you've done this dimensional reduction, you have the eigenvectors, you have the time series, you can do a power spectrum, and then climate scientists become really interested in this because usually there's a reason, right, why you have these large powers at longer time periods, because these are modes of variability that might be interesting to look at, like the El Niño Southern Oscillation, like the North Atlantic Oscillation, and so on, where I mentioned in the past, this usually has a period of around 3 to 7 years. This has more period of 20 to 50 years or so of different peaks. Now the problem, and that I want to just very briefly touch on for the assignment, is that the principal component eigenvectors, or EOFs that you plotted, were basically globally delocalized, right? So they're very difficult to assign to an individual process, whereas usually when we talk about climate modes of variability, we think about temperature variability in the tropical Pacific to Indian Ocean. So something very localized, right? ENSO would be more sort of center to East Pacific. North Atlantic Oscillation would be more on the northern Atlantic Ocean. The Indian Ocean dipole, IOD, would be more on the Indian Ocean Pacific. The cable variability would be in the North Pacific, and so on. So we think about these things as being localized, but the principal components don't deliver an eigenvector that would be localized. So it's very hard to interpret. So there's a trick to do this. So again, this is just what I said. They're highly delocalized, right? You have basically weights for each eigenvector everywhere. So how can we get something that is more interpretable? And there is a trick which is called rotations. Now, of course, it's just a different mathematical way of describing the data. So this goes back to the initial loop of unsupervised learning. We look at those principal component eigenvectors. And the eigenvectors look delocalized, so we think about ways to make them more interpretable in terms of a locally defined feature. And what we typically do to do this is to say we relax some of the orthogonality and uncorrelation constraints of the EOFs and the principal components, and introduce rotations. And this figure, I have to admit, I nicked from Wikipedia. I don't know the official source, but I think it illustrates this quite nicely on 2 dimensions. So if you had data that originally had loadings on, let's say, factor 1 and 2, and in our case, principal component factor 1 and 2, you want to rotate the data in a way that maybe most of those features, which in this case would be the grid locations of the the eigenvectors, that most of these features are oriented along one of the axes that you transform into. So you can try to find rotations that make specific grid locations be mostly associated with one of the components. Okay, and there are various tricks of doing this, and you could do this in an orthogonal fashion to keep an orthogonal definition of the axis, or you could do this in a non-orthogonal way, which makes it somewhat more confusing and difficult to interpret. So maybe the most common way of doing this rotation, especially in metrology, is the Varimax rotation. And the basic idea is, and again you will go through an example like this in assignment 7, is you take the original eigenvector and you multiply it by a linear rotation matrix, a linear transformation. And it then boils down to how this rotation matrix is defined to yield these sparser solutions, simpler solutions that are spatially more localized. And if you want to see many different types of criteria to then define what you actually try to maximize here, so that it always boils down to how do you find the rotation matrix. This will usually be some sort of maximization problem. There are many different ways to do this. There's a review paper I linked here focusing on the metrological side to achieve different ways of finding sparse solutions. And as I said, PCA Varimax, you can bang your head against the wall for quite a while to understand this. So I will not spend time on it, but the intuition is that you define this maximization criterion for the rotation matrix, rotated matrix of the eigenvectors. So this would be just V times R, which I labeled VR here, so that you maximize the sum of variance of the squared loadings. Okay, so please feel free to explore this more, but what you will see empirically, what it does is to simplify the structure by associating each grid point, each feature towards one of the components, towards one of the eigenvectors, and setting the coefficients or weights associated with an eigenvector for a particular feature equal, either moving it towards 0 or moving it closer towards 0, plus minus 1, sorry. And what you do by this is clearly that certain components will be much more associated with certain grid locations. So you get more localized features. Just to illustrate this here, this was no rotation. A big question is how many components you take into this rotation into account in the first place, because basically what you do is you redistribute variance between the components. You shift it around, you get a smoother eigenvalue spectrum as a result. But what you do is you shift this around, and this depends on how many components you include in your redistribution in the first place. So you could include, for example, 30 components, then you would get something like this. You can already see that there are still delocalized components, but it becomes somewhat more localized than what we had before. If you included 100 components, you would get something like this. It becomes more and more localized. Now you could already see that component 0 seems reflective of what I often refer to as the main mode of climate variability, which is the El Niño southern oscillation. So variability, it seems to be at least localized. You could look at the power spectrum as well. localized in the tropical East Pacific, where the ENSO is located. And maybe also component 3 might be associated with this more from a Central Pacific point of view. And as you do 200 components, it becomes even more localized. And now we have clearly saturated this color scale. So if you adjust the color scale, you see just about how localized this has really become. So a completely different picture to what you had before. And now you can really say, okay, this mode of variability or this component seems to really represent East Pacific variability, whereas this mode of variability is mostly associated variance over the maritime continent. This might be the Indian Ocean dipole, and so on. And again, you can look at power spectra as well to confirm what kind of variability you would expect from these modes, and timescales. So yeah, you will run through an example of this using causal discovery, where the first step is a PCA Varimax approach. You start from sea level pressure data, you dimension reduce it, you localize it using PCA Varimax, and then next week we will talk about how you can use causal discovery methods to then interpret linkages, interactions between these modes of variability over lagged relationships between those. And all this in assignment 7. I should mention there are many alternatives, including also autoencoders. So Pak pointed a nice paper out to me a while ago, which I only got to read over Christmas, so I thought I'd add it to this presentation, given that it got delayed. So if you're interested in some of these applications from a different point of view, using autoencoders as well, different methods, then do have a look. Okay, so next week, causal discovery. And otherwise, I'm already overrunning. So my question would be, if there are any questions. Certainly there are a lot, in principle. But any burning ones? Otherwise, we can also, once you address assignment 7, talk through this in the exercise class. Okay, good. Then thank you. And I will stop the recording again.